Okay, so first of all, I wish you a happy new year. So my name is Patrice Cartreau. This is my email address. I'm a full professor here at Centrale Nantes. I work in the same research department as Professor Kara. So this is the GEM research department, civil engineering and mechanics. And my field of research is homogenization of materials and structures. And currently I'm working on topics related to floating offshore wind turbines, especially the modeling of mooring lines, which are made in synthetic materials, and of electrical submarine power cable, which has a complex structure. So this part of course is within the course entitled Homogenization Methods for Materials and Structures. So I know that you have already had lectures with Professor Scara, and I discussed with him in order to minimize the overlap between what he presented to you and what I will present. So I will focus on architecture materials. Maybe some of you have attended the summer school in October on that topic. So maybe I will come back on some contents you already saw during this summer school. But I think I will enter in details to explain exactly how homogenization works for such kind of materials. So I think the overlap will be limited. So today it is an introduction course. So I wanted to start with some examples of architectural materials, and we have examples from nature. For example, here at the top you have a wing of a butterfly, and you can see that if we perform a zoom, we can see a tortoise shell type structure, and if we perform a zoom again, here you have some lamella, and if you look in more details, you can see another underlying microstructure. So here you can see that you have a hierarchical microstructural organization, and at each scale you have different types of structure. Here it is an example of bone, and depending on when you are looking, you can see that the porosity is not the same. The porosity is small in that part because the stress are important. And here, the porosity is larger because more or less this type of bone works in bending, and so we know that close to the midline of the bone, the stress are not important, so you don't need to have a large amount of material to sustain the load. And so when you are here, as the porosity is low, you have something which is stiff, but quite brittle. While here, the stiffness is low, but you can have a large deformation, and so there are some advantages compared to this. So it is an example of natural materials. A last example of natural materials. So here it is a marine sponge. So again, you can see the microstructure at different zoom scales. So you can see that you have main vertical and horizontal yarns, which are made from fibers, and sometimes you have also yarns in diagonal directions. And here, so it is honeycomb, and here it is nacre, which is the shell of oyster. Okay, and you can see lamella like that. So you know that. So I will put the slide on the hippocampus, so you can have access to the slides. You know that from many years, engineers were inspired by bio examples. And for example, if you look at a detail of the Eiffel Tower, you can see that you have some lattice structures like that. And if you perform a zoom again, you have you can see the detail like that. So if you have main beams here on the top and on the bottom, which are reinforced with diagonal beams, and you can see that it is very close to this type of structure. So we see that from natural materials we can build structure or materials which look like these natural materials. Other examples of artificial materials. So you have metallic foams, so with different types of cells. I will come back on that. Of course, you can build honeycombs of different types. For example, here it is with aluminium. And you can build also more exotic materials, such as this one. And do you know what is the main original feature of this material? You already see, did you already see this type of material, hexagonal or auxetic material? You don't know? The main feature of this material, do you remember?
Negative Poisson ratio.
Yes, you can have a negative Poisson ratio, because when you stretch the material like that, the circle rotates, and so you have an expansion in the orthogonal direction. So, of course, you have built the material in such a way that you recover such a negative Poisson ratio, but you can do it. So, depending on the objective of or the design parameters, it may be appealing to have a material with a negative Poisson ratio. And so, as you can see, and it is actually true when you deal with artificial materials, this material exhibits a periodic microstructure, which is an important property which will help us to define an homogenization approach which can take into account this periodic microstructure. So, thanks to the development of additive manufacturing, from few years now, there is a lot of variety of materials which can be built. These ones are known from some decades, I would say, but so here it is interesting because, as you can see, instead of having a grid like that, you build something which is like that. Etc. And so, when you think about the behavior of that material, when you have a tensile load in that direction, it is governed more or less by the stiffness of the vertical beams. But when you have something like that, of course, the load will be carried by the vertical beams, but when you arrive here, it will make the horizontal beam bend. So you will have a deformed shape like that, with this beam which works in traction and this beam which works in compression. And so you combine the stiffness in traction of this vertical beam and the stiffness in bending of this horizontal beam. While here you have just in the vertical direction the stiffness of the vertical beam. And if you look, and it will be the same in the horizontal direction, and here it is also the same. So it is an alternative to square periodic lattice, to have something like that, to make the individual structural members working differently to that period. So I will come back again on that, because we will see that depending on, at the local scale, the structural members work in traction or in bending, you get at the macroscopic scale an overall behavior which is more or less stiff, because you know that usually the stiffness in traction is much larger than the stiffness in bending. Okay? So please put that here, okay? And listen what I said. So you have different types of cells you can repeat to get this type of materials. So this type of materials are made of beams, okay? But you can also manufacture some materials. This one is again made of beam, but you can also manufacture materials which are made with shells. And here it is a simple, quite simple material, and this one is more complicated, as you can see from the basic set. Okay, so you can imagine a wide variety of materials, again, thanks to the development of additive manufacturing processes. And if we look at the details, you can see that due to this type of process, you see that we said that these are beams, but you can see the layers of the material. Here, the cross-section is more or less circular, okay? But when you look at joints, it's not so easy to imagine how or to which extent modeling such kind of joints as a network of beams is approximated or not. Okay, it's not so easy to see what we will give compared to the actual material you are able to build. Okay, so it's important to be aware of that because classically we will use models, but these models might be more or less close to the reality, which is like that. And you know that when you are using beam assumptions, for example, there are underlying assumptions, and the validity domain of a beam model is not infinite. Okay, so you have to be aware of that. Okay. So what is an architecture material? I will give you a definition. So here we will consider materials which are obtained by a repetition of a large number of basic cells, such as this one. The characteristic or the feature of the basic cell is that it is made with few structural elements. So here, for example, I already shown the basic cell. I think this is this one, yes. So this is the basic cell. So as I said, only few structural elements. And we can distinguish three different scales. The largest one is the scale of the part. So the order of magnitude is the meter. The order of magnitude of length of basic cell is a centimeter. And the cross section of each member of the basic cell, the order of magnitude is millimeter. Okay, so this is a way to define what is an architecture material. Okay? Any questions?
Yeah, what do you mean by microscopic behavior of 3D tech for a solid?
Okay, so macroscopic behavior means that we will substitute to this material, which is highly porous, a solid material whose porosity is 0, okay? And the objective is to find which properties this solid material should have in order that it globally behaves in the same way as this one. Okay? So we will look at what will be the properties of this material in order that it behaves globally as this one. Okay? So it means that we will consider this material, this heterogeneous material, as a homogeneous one, and we will look at the property of this homogeneous one to be equivalent to that one. Any other questions? So in this course, so the advantages of the architecture material is that you have only few design parameters. These are geometrical parameters, okay? You choose the skeleton material, which is the material you use for the structural members. And only with these few design geometrical parameters and the choice of the skeleton material, you can obtain a wide variety of controllable properties. And I will show later how you can say, I want these properties, and how I can explore the design parameters map in order to find the microstructure which enables to obtain the macroscopic properties I want to have. Okay, so it is an inverse problem. You say, I want to have such kind of macroscopic behavior, and you will see that we will be able to find the microstructure which leads to these macroscopic properties. So as I said, these materials are highly porous, so therefore they are very lightweight. And moreover, we talk about metamaterials or multifunctional materials because you can combine different properties. For example, you can look for materials which are both very stiff and, for example, who filter some waves in a frequency range you define a priori. Okay? You can also optimize the microstructure regarding stiffness and strength, for example, stiffness and conductivity, and so on. Okay? So this is why we say that it is more versatile than a classical material, because you have a material which can be good for one property but very low for other property. Here, thanks to the fact that you can make the design parameters vary and the skeleton material vary, you can obtain a wide range of material properties, depending on the physics you are considering. So it is very important. It is very important, and it also explains why these materials are more and more used in engineering applications. Okay. So what are the objectives of this course? So we have only 10 hours, so it's not so important. So here, this is what can be done classically in order to characterize the mechanical behavior of a structure of a material. Depends. Depends. I would say material. Okay, so for example, here you have a beam which is made by the repetition of a triangular basic cell. Here you have only one layer of this material. Here you have 2 layers, and here you have 3 layers. And each time you perform a 3-point bending test in order to determine the stiffness of the beam. And once you have the stiffness of the beam, you can identify the Young modulus of the equivalent Young modulus of the beam. Okay, so it is a way for characterizing the material corresponding to this triangular pattern. And you can do the same with another pattern. This time it is a square pattern. And again, you can perform this experiment and identify an equivalent Young modulus. But the problem is that, as you can see, if you change the number of cells in the beams, or if you change the shape of the cell, since we move from a triangle pattern to a square pattern, if you characterize the stiffness using this experiment, each time you change something, you have to build the part to perform the experiment, and so it takes time, and as soon as you change something, you have to repeat again. So the main drawback of such kind of approach is that it is not predictive, and so what we are looking for is a modeling approach in which, considering only the repetitive part of the structure, so it is one triangle or one square, you will be able to obtain these equivalent properties. And if you are able to do that, you can substitute the actual material by a homogeneous one and compute the beam response made with this homogeneous material directly. Okay? So this is the main advantage of homogenization approach, is that you can establish the link between the microstructure and the homogeneous equivalent properties. And so this is what we will do in that course. Okay? So the objective will be to modeling the behavior of architecture materials using homogenization. So we will analyze a basic cell, and I will show you how to define the homogenization problem. So what is the problem we need to solve on this basic cell? I will show you how to solve this problem using finite element analysis, for example. Or sometimes I will show you that we can solve also this problem using analytical approach. And from that, we will be able to obtain the equivalent properties of the architecture material. And we will study only linear elasticity. I will give you some information about strength, compressive behavior, etc., but it will be very spotty information. I will focus on linear elasticity. as I said, we don't have so much time, so I think it's better to focus on one topic and to do something which is quite consistent on that. Okay, so this is a figure which is in a book which has been published at in I think 97, so it is quite old. But this is an analytical approach which has been used to obtain the equivalent properties of honeycomb structure like that. And so there are analytical formula which provide the equivalent properties of honeycomb, which are quite old. Okay? So before to do that, I think it's important that you are comfortable with anisotropic elasticity. Okay, because I think most of you are comfortable with isotropic elasticity, but we will see that for such kind of material, the overall behavior might be non-isotropic, and so there are some non-classical situations or responses which correspond to non-isotropic material, and I think it's important that we spend time on that to see how it works. So I will make the assumption, which is very often fulfilled, that I forgot to say that we will focus on linear elasticity and moreover on in-plane linear elasticity. So as you can see here, when I have a honeycomb, I will consider the behavior in plane or in membrane. So this is why here I have only a 2D constitutive equation between the strains and stresses. Okay, so for example, of course it is true for a honeycomb, but I will make the assumption that in a given for two orthogonal direction x and y, the macroscopic behavior is of this form. Okay, so it is orthotropic, and it means that x and y are the directions of orthotropy. Okay, so we have an orthotropic material, and so x and y are the orthotropy directions. Okay? So in that, if we write, so in xy, the elastic behavior can thus be written as, so as you have here, So if the material were homogeneous, okay, you would have 1 over E, the Young modulus, minus nu over E, where nu is the Poisson ratio, 1 over E, and 1 over G, and G for a homogeneous material is isotropic material, sorry, is E over 2 times 1 plus nu. Okay? So if the material were isotropic, you would have this. But since the material is not isotropic, you have 2 different Young modulus, 2 moduli, Ex and Ey. G is not linked to E, so here you have Gxy, and here you have nu xy over Ex and nu yx over Ey. And so you have 4 different material properties which are 2 Young moduli, Ex, Ey, 1 Poisson ratio, because the second one is such that nu, since the matrix is symmetric, you have this property. This is why, once you know the 2 Young moduli and 1 Poisson ratio, you know the other Poisson ratio. Okay? So you have only 4 independent, I would say independent material properties, because the 5th one, the second Poisson ratio, is linked to, once you have these 4 properties, you can obtain the second Poisson ratio. Okay? You already saw such kind of matrix? You know what is an orthotropic material? You already saw that? No? So, at this moment, just consider that it is something which is a little bit more complex than isotropic material, because the Young moduli may be different. If they are different, you have 2 different Poisson ratios. And the shear modulus is not linked to the Young modulus and Poisson ratio. Okay? So you have 4 different independent material properties. Remember that for an isotropic material, only 2 independent material properties E, nu, and G, which is E over 2 times 1 plus nu. Okay? So only 2, while there you have 4. And we talk about orthotropic materials when we have 2 planes of symmetry. Maybe I can switch to something else. Yes. So, you have an orthotropic material. The constitutive behavior can be written like that, which is a little bit more complex than for an isotropic material, because for an isotropic material, you have only two independent material parameters, while here you have four independent material parameters. Okay, so it's a little bit different. And this is one difference. But there will be another difference. Now, suppose that instead of working in the X, Y directions, we want to see what happens if we consider the 1 and 2 directions. Okay? So now I consider two directions, 1 and 2, which are orthogonal, again, but with an angle theta between x and 1 and also y and 2. And the problem is, what will be the problem we want to solve is what will be the behavior in that plane. Okay, so now I want to obtain the relationships between the strain in the projected in 1 and 2 directions and the stresses projected on the same direction. Okay, so what we know is that, and the problem is to obtain how to find this. And this. And this scheme. So the direction 1 and 2 are not arbitrary. We know that there is an angle of theta between x, y and 1, 2. And so the question is, we know that, how can we obtain the constitutive behavior in this new basis? Okay? Here it is the constitutive behavior in the xy basis, while here we want the same behavior but in the 1, 2 basis. If the material were isotropic, can you say what we will obtain here?
The same.
The same. Okay? So, and we will check later, but if the material were isotropic, we will obtain here exactly the same as here. So with only the black writing without the red one, and we would obtain exactly the same. What we will obtain now, I don't ask to the detail, but can you say what will be the main characteristic of the matrix we will obtain here for an orthotropic material? Do you know that? Here, as you can see, we have something which is sparse, okay? Because we have a 2 by 2 diagonal matrix here and another term of the diagonal here. And so my question is, what will be the form of the matrix we will obtain here? So we will see that we will obtain something which is not sparse, and you will have non-zero terms here and here. Okay? This is the main difference between an isotropic material, because the isotropic material, the matrix is always the same, so it's a very strong property. But here, not only the matrix will be different there, but the zero term will become non-zero while we will perform the change of basis. So how to do that? Do you see how we can obtain this matrix?
Maybe you can take this one and multiply it by some rotation matrix that's like cosine and sine terms.
Yes. Only once?
You'd have to do it on both sides.
Mm-hmm. Yes, at the end it will be something like that. But we have to write it. And you will see that it is not so easy because it is not exactly a rotation matrix. Because the matrix we need should apply for second order tensor. Okay, it is not the rotation matrix which is usually used for vectors, which is a one order tensor. Here we have second order tensor, and so the rotation matrices we need to use are a little bit more complex. So, but it is a good starting point, okay? For example, if I would have something between, I don't know, ux, uy, which is I don't know, ux, uy, fx, fy, or fx, fy, ux, uy, and here, for example, a K matrix, a stiffness matrix. How you obtain this? This is what you just said, okay? Because here, this is a vector, here it is a vector. And so, what you will say, for example, you will say that fx times x plus fy is equal to f11 plus f22. And from this, you should be able to say that f1 is 1 times f, you agree? Or f times 1. And so f times 1, it is fx x times 1 plus fy y times 1, etc. And so you should be able to write that f1, f2 is equal to a matrix times fx, fy. And times 2. And so you can write that f1, f2 is equal to fx, no, x times 1, y times 1, x, y, 2, y times 2. This is a scalar product. Okay? So here, for example, you write it P. And so, what do you have? You have F1, F2 P, Fx, Fy. So Fx, no. Yes. So it is P times K Ux Uy, and Ux Uy will be P minus 1 F U1 U2. And so this is the new expression of K in the 1-2 basis. Okay? And we will denote it like that. K in the 1-2 basis will be that. Okay, so this is how it works. If you have vectors on the left-hand side and on the right-hand side. Okay, and you see that at the end you have something like that. P, K, P minus 1. And usually P minus 1 is also P transpose. Because this is a rotation matrix. You understand what I did here? You see, I have just written the definition of F1 and F2. F1 in the component in the one direction. So F1 by definition is F scalar 1 and F2 is F scalar 2. On the same way, Fx, you see that F, this is F. F is Fx times x plus Fy times y, etc. So since these two vectors are orthogonal, if you perform F scalar 1, this is F1 from here, and this is this expression from there. And the same with F2. Is it clear for you? Okay? So you can see that here you can obtain something like that. And once you know P, you write this. And here, since Ux and Uy it is exactly the same, Ux Uy is P minus 1, U1, U2. And thus, you get that. And so the new expression of K in the 1-2 basis is P, K, P minus 1. Okay? I have a feeling that it is is not so clear for some of you. Yes? Here? Yes, because here, the problem is that here you have F1, F2, and you want to make U1, U2 appear there. Okay, and what I have shown here is that I have written here for F, but it is true whatever the vector. Okay, so you have exactly the same for U. So you have also U1, U2, which is equal to P times UX, UY. Okay, and so if U1, U2 is equal to P times UX, UY, when you have UX, UY here, you multiply by P minus 1. Here you have P minus 1 times P, which is the identity matrix, and so you get UX, UY. Okay? Any other question? Yes?
Why did you write P equals is equal to P transpose in the end?
Because this is true if P is a rotation matrix. Because here we know that x scalar 1 is cos theta, cosinus theta, y scalar 1 will be sinus theta, x scalar 2 will be minus sinus theta, and y scalar 2 will be cos theta. Okay, so as you can see, the cos carré, cos square plus sine square is equal to 1. So the inverse of this matrix will be cos cos, sinus minus sinus, so it is the transpose of this matrix. Okay? So, you know the principle for vectors. So think about how we will generalize this for second order tensors. Please think about that. I give you a few minutes to think about this. But you see what I did. I have written f1 and f2 as a function of fx and fy. So here you have to do the same. You have to express the component of the second order torsor in the 1-2 basis as a function of the same components in a x, y basis. Okay? So please think about that. Okay? And in the following, to simplify the computation, we will denote cos theta as n and sinus theta as n. So you can perform the computation using these notations. So please think about how we can generalize what we did there for this relation, taking into account that we have second order tensors.
For example, if you try epsilon xx, okay, if you say that epsilon in the xy basis like that, it will you see that if you perform epsilon times x, for example, what it is a vector. So it is not a component, and it will be this matrix times 1, 0. Okay, so we get epsilon 6, the first column, epsilon. Okay? Sorry? Yes, yes, yes. Yes, yes. Free, but as I said, the main difference is that this is a second order tensor. Okay? Well, here it was a vector, which can be defined as a first order tensor. Okay? So you see that if you perform epsilon times x, you have this. So if you want epsilon xx, you have to perform an additional operation. So think about what you need to do to obtain epsilon xx, for example.
So a good way to start, maybe, is to be able to write what is epsilon xx, for example. Epsilon xx, how you can write it from epsilon. Okay? As I said here, for example, here, what I have written f1, it is f scalar 1. The question is epsilon xx, how can you write epsilon xx as a function of epsilon? And if you write it in matricial form, you see that the expression of epsilon in the xy basis is that. So how to extract epsilon xx from this matrix using proper operations. This is what we want to do. So here it was, here I could have written fx is f times x. Here, what should I write for obtaining epsilon xx from epsilon? And so once you will be able to answer this question, you will be able to define epsilon 1, epsilon 2, and so on. Maybe it's easier for you to answer the question from the matricial form. How can I obtain epsilon xx performing some operations on this matrix?
Epsilon xx minus epsilon y by.
Sorry?
Epsilon xx minus epsilon y by.
No. Here it is a simple scalar product for a first order tensor. Here it is a little bit more complicated, but it is that x times x because as you have two indices, and so you have to perform two scalar products. And so if you write it like that, here you will multiply by x, and here you will multiply by x transpose, which is 1, 0, like that. And if you do that, you will have epsilon xx, epsilon xy, and so if you perform this operation, you actually get epsilon xx. Okay? So in a general way, you have epsilon ij, which is I times epsilon in the ij basis times j, which is true for a second order tensor. Okay, it is true for the second order tensor. So we need to use these relations in order to calculate epsilon 1, 1, epsilon 2, 2, epsilon 1, 2, and so on. And so this is true whatever for a second order tensor. For any epsilon which is a second order tensor. So we need to calculate it. Okay. So for example, epsilon 1, 1 epsilon 1, 1 is 1 epsilon 1 1 is cos theta cosinus theta times x plus sinus theta times y. So I denote it mx plus ny. And so you get epsilon 1, 1, which is equal to mn, epsilon xx, epsilon xy, epsilon xy, epsilon yy times mn. Okay, epsilon times 1 is a vector, okay? So once you perform this first operation, you are led to a new scalar product between two vectors, and so the result is a scalar. So I will detail the computations. So here we have m epsilon xx plus n epsilon xy, m epsilon xy plus n epsilon yy, and so at the end we get m squared epsilon xx plus n squared epsilon, oh, it's not a vector, m squared epsilon xx plus 2 times mn epsilon xy plus n squared epsilon 1y. Okay, so it is more complex than for a vector, as you can see. But when you have operation like that, since this matrix is symmetric, you can see that the result is m squared times this term plus n squared times this term plus 2 times this product mn times this term. So, if you have understood that, it's clear that epsilon 2, so this time 2 is minus sinus theta x plus cos theta y, which is minus nx plus my. So you will obtain epsilon 2, which is minus nm minus nm and so if you have understood what I have explained, you will obtain n squared epsilon xx minus 2mn epsilon xy plus m squared epsilon yy. Okay? So I know that this is technical, but techniques is a part of scientific studies, you know. And so you need to be comfortable with that. This is the basics of second order tensor. So it's important to have this in mind. And at the end, epsilon 1, 2. So as I said, epsilon 1, 2 is that if I use this expression, epsilon 1, 2 is 1 epsilon times 2. And so 1 is nn. Epsilon is like that. Two is minus n m. So here it is not, since you don't have the same vector on the left and on the right of the matrix, you cannot use such kind of rules, and so you have to perform the computation. And so what we will obtain n. Okay. So we should find this. I'll just check. Okay, that's right. Okay. So the key expression is this one. Okay? And no. There is something wrong there. Remove the brackets there. Because this relation is true. And then you write this expression projecting, for example, here on the xy basis. And so if you write this, so please remove the brackets I have written before, and the true expression is this one. Okay, and then when we write this, we are writing 1 in the xy basis times epsilon in the xy basis times 1 transpose, times 1 in the xy basis. Okay, so we write this projected in the xy basis. Okay? Because, as you can see, if you write this projected in the x basis, xy basis, it's very easy because you have 1, 0 there, 1, 0 there, and so you get that. But here we write epsilon yy using this relation projected in the xy basis. And it is the same for epsilon 2 and epsilon 1, 2. So we can write, so we get, the problem is that here we have 2 times epsilon 1, 2. Okay, so it will be a little bit different. And also, since we have 2 times epsilon 1, 2 there, the starting relation was with 2 times epsilon xy. So here we have 2 times epsilon xy. This is why, for example, epsilon yy, we will have m squared here. Please stay here. The break is in 30 minutes. Okay? So here we have m squared times epsilon xx, n squared times epsilon yy, plus 2 times mn epsilon xy. So here we will have mn. For epsilon 2, it will be n squared, m squared minus mn. And for epsilon 1, 2, so we will have 2 times epsilon 1, 2. So it will be minus 2 mn, 2 times mn, and here it will be 2 times epsilon 1, 2, 2 times epsilon xy, so it will be m squared minus n squared. Just check. Yes, that's right. And so in the following, I will write it epsilon in the 1, 2 basis equals the transformation matrix T epsilon times epsilon in the xy basis. Okay, so this is T epsilon. Yes.
In the last part, when you write the m square minus n square, why do we have into 2?
Because you have 2 also here. Okay? It is a good question. Any other question? Yes?
As far as the one line over there, what you wrote over to the side, one, is that that's another form of what you were writing there, but why does that have brackets and that does not?
This is the tensorial writing, and this is the matricial writing. Okay? So here, it is true with epsilon, which is a tensor, and I and G, which are vectors. And then when you have to compute something like that, you have to project in one basis. Okay? So this is true whatever the projection basis you choose. And here I have chosen the XY projection basis. So I write here, how it works on this basis. Okay? So each vector is projected in this basis, and each tensor, an epsilon tensor, is projected in its basis. This is why here we have x component, xy, and so on. And here it is the x component of y, and here it is the y component of 1.
Where does the 2y, I'm so sorry, I'm bumping
No,
up.
no, no, no.
Where does this the 2y as the subscript comes from, and where does the xy on the
Where?
Yeah, why is it 2y again?
So this is this expression.
Mhm.
Okay? So here I write that epsilon 1 is 1 epsilon 1.
Mhm.
Okay? But in matricial form, this is a vector. Okay? So in matricial form, you will have 1 transpose times this vector.
Mhm.
And this vector is epsilon 1.
Mhm.
Okay? And this is true whatever the projection basis you choose, and here I have chosen the xy basis. So this is why I have added this. But you need to have the same
Wait,
projection basis.
Is it a xy, the very first one, not 2y?
No, x1.
That's why.
Oh, I'm sorry.
I was confused. Thank you, it makes sense now.
Any other question? That should be clear for you, because as I said, it is classical operation on second order tensors. So you should be comfortable with that. Okay? Even if I made a mistake there at the first time. But it's important, okay? But it is true also for a vector. You know that a vector is something which is intrinsic. Okay, y is a vector. It doesn't matter the projection basis you choose. And so the component might be cosinus theta and sinus theta, or 1 and 0, if you express 1 is a 1-2 basis. Okay? So the components of 1 are not intrinsic. While 1, when you write 1 like that, it is intrinsic. It is the vector. And even if you project it on different bases, you have always the same vector. And for the tensor, it is the same. Okay? You have a question? Okay. No, you should be good. But as you have seen, since for the strains we have the number 2 there, for the stress, the relation will be a little bit different. And so for the stress, we have sigma 1, sigma 2, sigma 1, 2 as a function of sigma xx, yy, and xy. So this term won't change, it will be again m2, m squared, n squared, n squared, m squared. But here we will have 2 times mn, minus 2 times mn, and here it will be minus mn, nn, and m squared minus n squared. Okay? And so in the following, I just checked, but it should be, yes, that's right. And so in the following, we will denote this as sigma in the 1, 2 basis, which is equal to another transformation matrix with an index which is sigma times sigma in the xy basis. Okay, so we have this. We have this. And we started with, so this was a relationship 1, which was epsilon in the xy basis was equal to something. I will denote it as S times sigma in the xy basis, and remember that S was like that, a 2 by 2 matrix, a non-zero term there, and 0 terms there. I will write it, it's not so difficult. 1 over Ex minus xy over Ex minus mu yx over Ey, 1 over Ey, and 1 over gxy. So this is S in the xy basis. So you see that epsilon in the xy basis is equal to T epsilon, no, epsilon in the 1, 2 basis on one hand, and also equal to S times sigma in the xy basis, and sigma is in the xy basis is no, I don't write it properly. So I should write epsilon in the 1, 2 basis is equal to T epsilon, epsilon in the xy basis, epsilon in the xy basis is equal to S in the xy basis times sigma in the xy basis, and sigma in the xy basis is minus 1 times sigma in the 1, 2 basis. And so here it will be S in the 1, 2 basis. It is the constitutive behavior in the 1, 2 basis. So it is T epsilon S T sigma minus 1. So I won't perform the computation on the board because you have to multiply 2 times 3 by 3 matrices, so it's cumbersome. But what you have to retain is that the constitutive behavior in the 1, 2 basis is of this form. And you see that T sigma and T epsilon are not the same because of the coefficient 2 in the strain vector. Okay? Any question? So I will show you the expression of S, okay, and you will see that S is a full matrix. So here you have the different numbers for S. So as I said, S is a full matrix. The non-zero terms there this time are not zero. And of course, it is symmetric, okay? So S12 equal to, these 2 terms are equal, these 2 terms are equal, these 2 terms are equal. And you have this. So, you can check that if you come back to the case of an isotropic material, so S expression in the 1-2 basis is known. One can check that for an isotropic material, namely Ex equal to Ei equal nu xy equal nu yx equal nu, and Gxy equal E over 2 times 1 plus nu. Whatever theta, whatever theta, S11 is 1 over E, S11 equals S22 equals 1 over E, S12 is minus nu over E, S33 is 2 times 1 plus nu over E, and S13 equals S23 equals 0. I did that, and trust me, it works. But we can try, for example, S11. If you look at S11, if you say EX equals EY equals E, S11 will be M up to the 4 plus M to the 4 over E, plus M2 N2, 1 over G will be 2 times 1 plus nu over E, minus 2 times nu over E. So here it is 2 times over E, and so you get 1 over E times M up to the 4 plus M to the 4 plus 2 times M squared N squared, which is M squared plus N squared squared, which is 1. Because M is cos theta and N is sinus theta. Okay, so you see that it works. And for example, S13, for example, is minus 2 Mn plus times mu over E minus 1 over 2 times J. So this is minus 1 over E. So it is actually 0. So it works. Okay, you can check that for an isotropic material. You obtain that this matrix is constant, and with 1, 3, 2, 3, 3, 1, and 2, 3, a 3, 2, 0 coefficients. Okay? But for a more general case, you see that starting from something which is diagonal by blocks, you obtain something which is full. Okay? However, for a non-isotropic material, S depends on theta, and for theta different from 0 or 1/2 of pi modulo pi, the matrix is full. So what does it mean? I will write or pi or 3 half of pi. The matrix is full. What is the physical meaning of that? As I said, usually you have a 2 by 2 matrix here and a diagonal term there. So the only new feature of a full matrix are the non-zero terms S13, S23, S31, S32. So can you see what is the physical meaning of this? What does it mean? For example, S13 different from 0. What does it mean? So it is also S31, okay? S13 equal S31 different from 0. Can you tell me how we can see the consequence of the non-zero, the fact that this term is non-zero? So, for example, consider a tensile test. So consider a tensile test in the one direction. Okay, so what does it mean? It means that sigma sigma 11, sigma 22, sigma 12 is of the form sigma 11, 0, 0. If S13 is not 0, you get that epsilon 11, epsilon 22, 2 epsilon 12 will be equal to S11, S21, S31 times sigma 11. And so, what do you have? You have 2 epsilon 12, which is different from 0. And so, what does it mean? It means that if you perform a tensile test like that, with sigma 11 like that, so the one direction is like that, the 2 direction is like that. Usually, if 1 and 2 are orthotropic direction, you should get something like that as the deformed shape of the sample. But since 2 times epsilon 12 is different from 0, you will get something like that with a shear strength. And so the deformed shape will be like that. Deformed shape. So you have shear tensile coupling. Okay? So here it is a tensile stress which leads to a shear strain, but you can have the reverse also. So you can consider a shear test, and for a shear test, you will get non-zero strain in the 1-1 and in the 2-2 direction. So it will be the same. So I just finish with that. On the same way, the reverse, I mean shear tensile coupling will be obtained from a shear test So this time, sigma 11, sigma 22, sigma 12 is equal to 0, 0, and just only the 1, 2 component is non-zero. And so in that case, you get epsilon 11, epsilon 22, 2 times epsilon 12. It is the third column of the matrix. So it will be S13, S23, S33 times sigma 12. And so this time, what do you have? So again, 1 and 2 are like that. You have shear stress sigma 1, 2. Again, if you don't have this coupling, you should have a deformed shape like that. Without coupling, you will have something like that. I mean that the length here will be equal to the initial length, and the length there will be equal to the initial length. But since you have coupling, the length will change here, so you will have something like that, and the length will change also here, because epsilon 22 is not 0, and so you will obtain something like that. So here you will have L1 times 1 plus epsilon 11, and here you will have L2 times 1 plus epsilon 22. If L2 is there, and L1 is the initial length in the 1 and 2 direction. Okay? So classically for a shear test, you have a shear strain, but here you have additional strains corresponding to the length variations in the 1 and 2 directions.
What is that word say below the equation S13 above the sentence you wrote above that matrix?
Tensile test in the y direction. Any other question?
In the green,
Sorry?
in the green, writing with your writing, green.
Speak louder, please.
In the green line here. what is
Deformed shape.
Deformed.
Yes. Okay? So I think I will stop here. So again, I will give you the slides, maybe tomorrow, because there are additional slides after this one. Okay. Thank you. I can, yes? Oh, I just, that one. Okay.